Yeah, you can ask me questions, whatever the doubts you have. This is the time to interact. Now, face-to-face interaction is always good. Please ask whatever the questions you have. Any doubts, clarifications, which you did not understand, or something which was not clear from my explanation. Some of you, please speak. If you have any clarifications, please ask. You have 1 hour time to discuss. Okay. There is a one person's Simran Patel asked the question. Please explain nuclear magnetic moment. See, it is nuclear magnetic moment is mu. As I told you in the class, nuclear spin can be considered like a tiny magnet. A tiny magnet means like a bar magnet. Imagine you have a north pole and a south pole in a bar magnet. Similarly, if you consider nuclear spin as a tiny magnet, as you would have understood from your high school days, when I talk about magnet, we have a magnetic field, and we can also discuss about the property of the magnet called magnetic moment. It is an internal property which is denoted as mu. It is a vector quantity. Mu is for the spin, which can be treated like a tiny magnet. The spin angular momentum has a property which is called magnetic moment. And this, of course, we also can define in terms of magnetic moment mu. It is an internal property. You have any, are you clear with me? So many of you are there. If you have any other questions, please ask. Okay. There is a question from Chetan Patel. Sir, the language of our lecture is difficult to understand. Okay, sir, please ask me what is that you try, it was difficult for you to understand. What is the language of the lecture? What do you mean by that? See, I speak in English. Is that the difficult for you? Is understanding my English is difficult? Okay. Anyway, I'll come to the explanation of the rotating frame. Before that, there is a question from Chetan Patel. Said the language of our lecture is difficult to understand. Please tell us what is that you are finding difficulty. You mean the English language or the language of the science which I'm explaining? What is that you cannot understand. Chetan, you can tell me. Okay. Now there is one question called concept of rotating frame and also bulk magnetization. Both are there. Two questions have been asked, which I am trying to explain now. First of all, we'll start with what is called a bulk magnetization. Remember, if you take NMR sample in a tube and put it in a magnetic field, there are lots and lots, millions and millions of nuclear spins. They all start aligning in the magnetic field. Some align in the direction of the field, some align in the direction opposite to the direction of the magnetic field. Each individual nuclear spin, in NMR jargon, we call it magnetic moment. Okay. Now, as I told you, magnetic moment is a vector quantity. Mu is a vector. I can resolve it into three components. If it's a three-dimensional vector, I can resolve into x, y, and z axis, all the three components. Okay. So now, if I resolve into three components, mu z is along z magnetic field direction, x and y is in a direction perpendicular to magnetic field. But what happens in the mu x and mu y, in the xy plane, if there is one vector, let us say in this direction, there is always another vector in the opposite direction because millions of nuclear spins are there. So as a consequence, you can think of a situation, if one vector is in this axis, and equal and opposite magnitude, another vector will be there in the opposite direction. So there are so many millions and millions of magnetic moments, vector components in the xy plane. If you take an ensemble average of all those things, take addition of all those things, it becomes zero. Because whatever the vector is in this direction, that will be there in the opposite direction also, another vector. So it becomes zero. But what about z-axis? Mu z component, z component of the vector. There is only one vector component that will be there. So all z component vectors is always in the same direction. They all get added up. That will not get nullified. Whereas the xy components completely get nullified. There is no magnetization in the xy plane. This is for the nuclear spins orienting in the direction of the magnetic field. So there is all these nuclear magnetic moments which are along the z-axis, the component of them, they will add up. What did I say? Each spin is a tiny magnet. A small magnetic field component here with one spin. Now millions and millions of spins, this magnetization or the magnetic field along this axis, z-axis, keep on adding up. They will not get cancelled out. They all add up. Hmm? Hello? Any doubt? Hello? Any doubts? Okay, let me complete it. So you add up all the magnetic moment components along z-axis. No, I am speaking English. Okay, there was a doubt there, so somebody asked which language. Okay, so z component magnetization along this axis get added up all the components of the magnetization, all the components of the magnetic moment vector. We call this as another tiny magnet. All magnets, small magnets add up and give rise to another magnet. And then this is for the magnetic moment in the z-axis. What happened to the spin aligned in the direction opposite to the field? Identically, xy components become 0. Then all the components of the vector in the direction opposite to magnetic field will again add up. Then this will be another small magnet. All added up gives us a small magnet. So now we have two magnets. One tiny magnet in the direction of the field. Another tiny magnet in the direction opposite to the field. But remember, I explained to you about what is called Boltzmann population distribution. According to that, there are more spins in this direction than in this direction. More spins in the direction of the field than in the direction opposite to the field. As a consequence, this Z component vector added up will have magnetization, tiny magnet in this axis. Another magnet in the opposite direction is there. But then this magnet has a larger value compared to the magnet in the opposite direction. Since they are vector quantities, two of them, one in this direction and one in this direction, now they start adding up. But there is more in this direction and in this direction. As a consequence, there is a differential component of the magnet. Magnetization. This difference gives us a small, tiny magnet, which we call as a magnetization. This is called bulk magnetization because different nuclear spins, which are different magnetic moments, oriented both in z-axis and along minus z-axis. When we take xy components, they get nullified, and only we have addition along z-axis and minus z-axis. Between these two, there is a difference because of Boltzmann distribution. As a consequence, small magnet will be there along z-axis. That is called bulk magnet. That is called a magnetization or called bulk magnetization. Well, this is as far as the bulk magnetization is concerned. Now, somebody asked me a question about rotating frame. Okay. So, what is the rotating frame? Remember, you are going to apply a radio frequency pulse and bring the magnetization to the XY plane. You are applying a RF pulse. RF pulse itself has a magnetic component. You can consider this RF component, which has a magnetic component, which tilts the bulk magnetization to XY plane. But earlier what happens, this nuclear spins will be rotating along z-axis, persisting along z-axis. What is the magnetic field along this axis? It is the main magnetic field B0, strong magnetic field. Moment you bring the magnetization to the XY plane, they will start persisting in the XY plane along this x-axis or y-axis, where the magnetic field is dictated by the RF field, RF pulse, which are applying. This RF pulse is very, very small compared to main magnetic field. Once you are entering in the XY plane and see the precision of the magnetization or nuclear spins along this axis, that means you are entering into a frame called rotating frame. When you are entering into the rotating frame, you can imagine this magnet, strong magnet, is absent as far as the nuclear spins are concerned. This is an advantage for us because when you have this magnetic field absent, we are considering only magnetic field along the XY plane. Because we are in the rotating frame, the small magnet and precision frequency is also much smaller compared to this one. That's what you can imagine. The reason is, advantage of this is, you don't have to worry about P naught or omega naught. You always can concentrate only on the frequencies corresponding to RF magnetic field, which is much smaller. As a consequence, that V naught component can be treated to be absent in the rotating frame. Or in other words, I give you an example like this. You must have seen what is a giant wheel. A big giant wheel will be there in some of the exhibitions you would have seen. It keeps on rotating like this. That is one frame of reference. If a person sitting outside the giant wheel, for him, he is in a laboratory frame. This is the rotating frame. It is rotating. It looks as if this is rotating as far as the person standing outside. Now, what you can do is, if let us say from here, you want to shoot a gun here to somebody, you cannot identify who it is because you are rotating. It is very difficult to find out who it is. On the other hand, instead of standing here, you jump onto the giant wheel in one of the cabins of the giant wheel, which is undergoing. Now, for a person sitting in the giant wheel, it appears as if it is not moving. The person who is sitting in the next cabin appears stationary for him, as if it is not moving. Then he can aim at that person very easily. So what does it mean? In the rotating frame of reference, when you go, it appears as if it is stationary, because when you are in the outside field, rotating field here, it was rotating. This is the laboratory frame, this is a rotating frame. But when you enter rotating frame, it appears as if the position is not there. It is static. It is stationary. That is the concept of rotating frame. There's a lot of advantages for you to understand the basic concepts of NMR. Is it clear to you? Hello? Is it clear to you? Somebody is asking question. Is it possible to get peaks of this course? A question. What is the meaning of peaks? PYQS. I don't know what you mean by that. But the entire course, the YouTube version of this is available on the web. You can download it. The entire course is available. All lectures are available. Okay. We'll go to the next question by the protons which are shielded appear upfield. That is, they resonate at lower frequency. Shielded protons have more local magnetic field around them to due to electrons. Then why don't such protons require high frequency? It's a very good question. Okay. Asked by one question by name J. Sarthak. It is a convention. Let me open the slide, open that slide and explain to you. That is better for you to understand. Bharat, can you please turn on the sharing? It says I cannot share it.
Yes, sir.
Okay. Okay, this question was asked by one person by name Sarthak. Sarthak, now please see this, what I am explaining here. This is shielding and de-shielding is a terminology which is little confusing. What do you mean by low electron density and high electron density? Is like this. When there is a nuclear spin here, this is the electronic charge. If there is an electronic charge around this nucleus is less, it is less shielded. That means you should experience weaker magnetic field. You are right. Less shielded means weaker magnetic field. On the other hand, high, what is this? Okay, on the other hand, if you have high electron density, as I have written here, the charge density is much stronger compared to this. That means it is more shielded, that it experiences stronger magnetic field. Your question is correct. When it experiences stronger magnetic field, it should resonate at the higher field, right? When more shielded, it should resonate at the higher field. But there is what is called a confusing terminology. This is just, I know, I understand. For everybody who tries to understand, this terminology is confusing. For the reason, with higher shielding, the proton resonates at higher field, lower frequency, which should be opposite in principle, according to way we understand. But conversely, it is also true. Higher de-shielding, the proton should resonate at a lower field, higher frequency. This is what we are observing. Why this happens is because this terminology evolved from the days of what is called continuous wave NMR. There was no pulsed NMR those days. We used to keep the field constant, keep on varying the frequency of the radio frequency. Then what happens? At a particular field, we used to get a resonance. Higher the magnetic field, we used to get a higher resonating frequency. And lower the magnetic field, it used to be lower resonating frequency. The CW terminology was, it was a scanning from one end to other end. Depending upon whether you go from left to right or right to left, your resonating frequency increases in this direction and decreases in this direction. And this confusion of the terminology started from the CW days. When the Fourier transform NMR started with the pulse NMR, this terminology continued. As a consequence, it is a bit confusing for you, saying that higher field should resonate in principle at higher frequency, but it is not happening. So this is only a way of mentioning, way we discuss. You understand? This is only a confusing terminology. Don't get disturbed by this. Are you okay with this? Hello? Sarthak, did you understand? Is it clear for you? This confusion terminology. Simply understand this has evolved from the days of CWNMR and the same terminology is being maintained. But what you have written is correct. Higher shielded means we should say higher magnetic field should higher resonating frequency, but it is just interpreted in the wrong way. That's all. Because of the understanding started from the CW days. Sarthak, are you okay? Any other questions? Anybody else? You can also type your questions. like others did. Yeah, please unmute yourself and ask. You're free to unmute yourself and then you can ask the question or type here. How many weeks are over? How
Four
many
weeks.
lectures?
4 weeks. 4 weeks.
So 4 weeks. So that means a lot of lectures have been already completed. So any other doubts? Please ask the questions if you have any. Any doubts? This is the time you can directly ask. We can meet face to face and clarify the doubts. Participants, please ask the questions. Yes, see, LPT office is telling live session will end by 11:30. So please ask your doubts. Clarify any of your doubts now. Are you all comfortable? You can also suggest me if there is anything else if you want us to cover in the next semester, we can do that. Okay. So shielding and de-shielding is same for aromatic and anti-aromatic compound or not? No, it is not true. You can find out aromatic protons because of the aromatic ring current effect. Generally, they come at the downfield around 6 to 7 ppm. But in the anti-aromatic case, it can be different. It can go even the other way also. The chemical shift need not be always like comes in the aromatic region. In some examples, it can go even high field, even beyond zero also. It need not be same. Okay, please use simple language. Okay, I don't know what simple you language you want me to use in explaining science. Okay, shall I explain? See, if you have to understand NMR, some technical words we need to use. We cannot avoid that. Okay, he says your language is very difficult for understanding. So use simple language for explanation. Okay, for Simran, what do you want me to explain? You ask, tell me something. Okay, coupling and coupling constant. You want me to explain coupling and coupling constant? All right. I'll explain in a very, very simple way, simple language. But in any case, you cannot avoid technical terms. You can't anticipate. See, coupling is a NMR terminology. Coupling constant is an NMR terminology. So I will explain to you in a different way, as simple as possible. I'll open the slide for you. Okay, are you seeing the slide now? Are you seeing the slide now? Okay. J coupling mechanism goes like this. J coupling is a transfer of magnetization from this nuclear spin to this nuclear spin mediated by covalent bond. Please understand, the magnetization, also we call polarization of the nuclear spin, is transferred from one spin to other spin through covalent bond. It means for coupling to see, there must be a chemical bond. Without chemical bond, there cannot be J coupling. See, how the J coupling happens? This is not important for you. I'll show you here in next one. Okay. Some few terms of the couplings I will explain. It is not only covalent bond mediated, it has several other features. For example, you can see the coupling between this to this proton mediated to this bond, this and this. There are 3 bonds away and there is a coupling. And here, for example, this proton to this proton, direct interaction, there is no coupling. That is a different type of coupling called dipolar coupling. But you don't worry about it. Since it is not mediated through covalent bond, this is not J coupling. It is not possible. For covalent bond is necessary. It is necessary for coupling, J coupling. And this is also not possible directly. Whereas through covalent bond, which I explained like this, is possible. See, see, through this is allowed. This is not allowed and this is not allowed. All right. And of course, these are some of the important things, not important things, but you wanted what is a coupling. I'll explain to you what is a coupling. See, for example, if I consider single nuclear spin, how many possible orientations are there in a magnetic field? They are called two spin states. For one nuclear spin, we have one nuclear spin orienting some along the direction of the field, some in the direction opposite to the field. Remember, I said this is called a alpha state and this is called a beta state. There are two spin states. And this has a different energy and this has a different energy. Remember that. There is only one nuclear spin. What happens if there are two nuclear spins? Let us consider what are the possible ways they can interact. One, when the two nuclear spins are there, each spin has two orientations like this. Spin 1 has up and down, spin 2 has up and down. Spin 1 has alpha and beta states, spin 2 also has alpha and beta states, two states. Individually, there are two states. Now, let us say there is an interaction, meaning the magnetization or the spin polarization or magnetic energy you call it from this nuclear spin to go to this nuclear spin through a covalent bond. That is called interaction. Two nuclear spins are interacting. Then what are the possible orientations you can think of? You can think of four different possible orientations. Let me explain to you what it is. Before going there, let me tell you. When both are interacting, there is a possibility. When this is alpha, this is also alpha. When this is alpha, this can be beta. There are two orientations. When this is beta, this can be alpha. When this is beta, this can be beta. Now, you have four orientations. Alpha alpha, alpha beta, beta alpha, and beta beta. These are four different energy states. Remember, if I say, see this nuclear spin, it can see this in two orientations, alpha and beta. This will see this spin one in alpha and beta, two orientations. Please see, understand. I want to explain in a simple way because my friend is asking in a simple language. If I consider spin 1, this will see spin 2 in the orientation upwards or downwards. That is, it has two energy states called alpha and beta. Consider spin 2. This also has two orientations, spin state up and spin state down. Two energies, this is called alpha and this is beta. So there are four combinations you can think of. In a simple language, you look like this. If I see proton X, let us say X and A are the two protons which are coupled. X will see proton A in this orientation, let us say upper orientation in the direction of the field. Then it has one energy. Proton X can also see proton proton A in beta state. See, remember proton X will have proton A in alpha state, proton proton A in beta states. That means it has two energies. When it is alpha, it has one energy. When it is beta, it has another energy. When it is beta state, the energy is like this, higher frequency. In the alpha state, energy is the lower frequency. Why? I have already explained to you in one of the classes. Because of minus mu dot h, minus is there, beta is minus half into minus half is plus. So this is positive, whereas this will become negative. As a consequence, when proton X sees proton A in beta state, it has higher energy. When the proton X sees proton A in alpha state, it has lower energy. So that means there are two energy states, we'll get two peaks correspondingly. So for proton X, you will get two peaks. What about proton A? Exactly. Proton A will see proton X in alpha state, proton X in beta state. Again, two energies. So this also will be giving two peaks. So proton X will give two peaks because of proton A in alpha and beta states. Similarly, proton A will give two peaks because of proton X in alpha and beta states. So each of them will be two peaks. A will give rise to two peaks, X will give rise to two peaks. It is because there is an interaction. They have orientations, alpha alpha, alpha beta, beta alpha, beta beta. These are four energy states. We have four frequencies. And you measure the separation between two peaks of A, this corresponds to coupling constant. Similarly, for this chemical shift, measure this separation, this will be also coupling constant. Remember, I told you, interactions in NMR are always mutual. If A is coupled to X, X is also coupled to A. That means if this is a doublet, this is also a doublet. Then if this separation is JAX, this is also JAX. So measure this separation, you will get coupling constant. Similarly, measure this separation, you get coupling constant. Both are same. At the center of this doublet, you get chemical sheet of one proton. At the center of this doublet, you get chemical sheet of other proton. It's a simple example of what is a coupling. What is a coupling constant? For two protons are coupled. Remember, coupling is a transfer of magnetization from one proton to another proton mediated through covalent bond. How it happens, you can understand in a different way. The nuclear spin of this proton will make this orientation of the electron surrounding it. This electron in turn go through the covalent bond, makes this electron orient opposite. Or since because both the electron has a negative magnetic moment, they will align in the same direction. This will make this nuclear spin orient opposite to this. That means this nuclear spin through its electron gives magnetization to this electron and to this nucleus. So the two nuclear spins will exchange energy or transfer energy mediated through electrons involving covalent bond. This is what is called coupling. It is called scalar coupling because it's not dependent upon the direction. It is simply a number. It is a scalar quantity. If I say coupling constant, separation between these two is a coupling constant. If I say it is 10 hertz, it's simply a number, no direction. So it's a scalar quantity. So remember, coupling constant is just a number, is a scalar quantity. The number could be positive or negative, or it can be zero, no problems. But it's just a number, it is a scalar quantity. And this separation is coupling constant, and the why it is being split is because of the transfer of magnetization between one nuclear spin to other nuclear spin through covalent bond, that is called coupling. Are you all okay with me? One person asked me a question. Hello? Did you understand? Who is that who asked me the question? Explain coupling and coupling constant. Who asked this question? I don't know. Sakshi, did you understand this?
The question was asked in YouTube.
Oh, YouTube. How do I know who is that asking YouTube? Okay, doesn't matter. Oh, she said yes, sir. That's fine. All right. So there is one more question here. Can you explain in Hindi language? Very good. Our Sandeep has joined now. He can explain what is coupling and coupling constant in Hindi. Sandeep, can you please explain in Hindi for them? Because I don't know Hindi.
Yes, sir.
Sandeep is a Hindi person. He will explain.
Yes, sir.
हिंदी में बोलो.
Okay. Are you hearing?
I think she must be hearing. You can tell.
या क्या होता है कि एक न्यूक्लियस में दो जैसे स्पिन हाफ न्यूक्लियस है. स्पिन हाफ मतलब आई वैल्यू 1/2. तो उसमें क्या होता है कि देयर टू एनर्जी स्टेट्स होते हैं, मतलब एनर्जी लेवल. तो एक को बोलते हैं अल्फा स्टेट, अनदर इज बीटा स्टेट. तो लोअर एनर्जी मतलब जो ग्राउंड स्टेट में है, कम एनर्जी का है, दैट इज कॉल्ड अल्फा स्टेट. और जो हायर एनर्जी का है उसको बोलते हैं बीटा स्टेट. सो अगर एक न्यूक्लियस है, एक दूसरा न्यूक्लियस है, सपोज स्पिन हाफ ओनली, बिकॉज वी आर टेकिंग एग्जांपल. इसका मतलब ये नहीं कि स्पिन हाफ ही होना है. इट कैन बी स्पिन 1 भी हो सकता है, 3/2 भी हो सकता है, या कोई भी हो सकता है. बट एग्जांपल ले रहा हूँ स्पिन हाफ का, क्योंकि वो सिंपल है समझने के लिए, बट वो सबके लिए सेम रहेगा. तो अगर एक है स्पिन हाफ का न्यूक्लियस, दूसरा है स्पिन हाफ का न्यूक्लियस, सो उसका अल्फा एंड बीटा स्टेट्स होते हैं दो, दूसरे का भी अल्फा और बीटा स्टेट होता है. तो अगर वो दोनों इंटरैक्ट करते हैं, मतलब इंटरैक्ट मतलब कि उसके इंटरेक्शन के लिए कुछ एक क्राइटेरिया है, मतलब एक लिमिट की अगर ये कंडीशन है तो इंटरैक्ट करेंगे, मतलब दे आर close, like 3 bonds, 4 bonds, maximum or 2 bonds. Let's say 1 bond is very good. Okay, so 2 bonds, 3 bonds, they only where coupling possible है. So क्या होता है कि उसके लिए फॉर एक न्यूक्लियस के लिए कोई भी अगर ले लिया x और a, सपोज 2 है, तो a के लिए x का एक एनर्जी स्टेट है अल्फा स्टेट, एक है बीटा स्टेट, तो वो दो एक्सपीरियंस करता है, तो अल्फा स्टेट की वजह से उसका एनर्जी स्टेट से थोड़ा सा जे के वैल्यू में अगर बोले तो फार्मूला में रखने से हमको पता चलता है कि वो 1/4 × 2 1/2, तो 1/2 जे होता है, ठीक है। सो बिकॉज ऑफ बीटा स्टेट इट विल शिफ्ट वन साइड फ्रॉम द सेंटर, वो उसके सेंटर फ्रीक्वेंसी से एक साइड को स्विच करेगा आधा हाफ जे, और अल्फा स्टेट की वजह से दूसरे साइड में लेट्स से पॉजिटिव साइड, तो वो हाफ जे शिफ्ट करेगा। सो टोटल दोनों तरफ से सेंटर में हाफ जे दिस साइड, हाफ जे दिस साइड, सो वो हो गया 1 जे, सो दैट इज कॉल्ड जे मींस कपलिंग। सेम थिंग दूसरे के लिए भी होगा, जो एक्स स्पिन है वो वैसा ही एकदम बराबर एग्जैक्टली सेम एनर्जी डिफरेंस एक्सपीरियंस करेगा एक ही वजह से। तो इसके लिए एक्स भी दो एनर्जी स्टेट्स आएगा सेंटर से, हाफ जे इधर शिफ्टेड, हाफ जे दिस साइड शिफ्टेड। सो दोनों क्या होता है कि यू कैन नॉट से कि वो किधर शिफ्ट हुआ, क्योंकि दोनों तरफ आधा आधा हुआ, इसलिए इसको बोलते हैं स्केलर कपलिंग है, कि इसका कुछ मैग्नीट्यूड होगा, साइन भी हो सकता है, बट वो ये नहीं कह सकते कि वो किधर शिफ्ट हुआ है। सो ऐसे कपलिंग आते हैं। सो अगर स्पिन 1 है तो उसके हिसाब से फिर उसके अल्फा उसमें 3 एनर्जी स्टेट होंगे, तो वो एक उसका वो अगले वाले को 3 लाइन आएंगे, क्योंकि वो 3 एनर्जी स्टेट एक्सपीरियंस करेगा।
Okay.
क्लियर?
Hello, is it clear for you? Who asked me this question? So, I don't know who asked this question.
हाँ वो बोला ओके सर कुछ।
Okay, okay, good. All right. So, there is one question from one person who says, Sir, why there is no assignment solutions after assignment completion of this course? I don't know what to answer for this. Sandeep, you know, are we giving answers for that?
हाँ
Are we giving answers for the assignments after the completion?
आंसर्स वी कैन क्यों, अदरवाइज वी कैन डिस्कस एक्चुअली इन ऑनलाइन सेशंस ओनली।
Okay. So what you can do is, hello, Mr. Jignesh, come back next time in the next session. Come with your doubts, whatever the assignment, what you have completed. If there are, if you require solutions, we will try to give you them. I don't know what is the NPTEL no, procedure, whether to give the answer after or not. That I don't have the answer. But I can give you the answer when you come for the next live session. Come back. I will be there and Sandeep will be there. We will give the answer for you.
If NPTEL don't objection, so let after that course we can send them personally,
Yeah,
someone
we can,
requested by
we can
mail.
send you the
We
personally.
can upload, sir.
Personally, if someone request on mail.
You can do one thing, you can send your email after this course is over, because there is some assignment, number, marks, everything will be given. After this, we can mail you the answers. Simran, not Simran. Who is this? Jignesh. You can give your email after the course, we'll give you the answers. Okay, he says. Okay, done. So any other doubts? Today it is very good actually. 15 people participated. Full session today. Okay, Jignesh, thank you. Okay, thank you. You say mail, send your email to Sandeep. Sandeep can, after the course, he'll
Yeah,
give
I
you
will
the.
write my email here, so they can write me
Yeah, can you write your email? Sandeep, Jignesh, note down his email ID. Sandeep will give you answers after the course for all the assignments.
once it is over.
Yeah. Write down, all of you, please write down this email ID of Sandeep. He's another expert in NMR. He will give you all answers.
Even if they are interested, we can explain also, like
Also.
with explanation.
Yeah. See, another thing, you don't need to worry about live session. If you have only one or two specific doubts or questions, you can always write to us.
Huh.
Don't ask us to repeat the course. Only one or two questions.
Yeah. No, they
Specific
can ask
questions.
personally, so we will
Personally,
make
you
them
can ask.
understand.
Yeah. You
Huh.
can send an email personally. One or two specific question, we can answer it. Is it okay? All right. Good. Any other questions? Now time is getting over. At 11:30 we have to stop this because some other session for some other course will start. We have to stop at this 11:30. If you have any other questions, ask me. Otherwise, we have to end this session.
For any doubt, you can write a mail, so we will provide you the
Yeah, that's also we can do
explanation.
that.
Hmm.
Anybody else? Any questions? So what do we do, Bharat? Time is up.
We can wind up the session, sir.
Okay. So thank you all participants. Thank you, Sandeep, for
Thank
having
you, sir.
joined now. All right. So we will meet in the next live session. By then, you come with set of prepared questions. We can see what to do. Thank you all.